The Death Star is a mobile battle station owned and operated by the Galactic Empire, equipped with the galaxy's deadliest weapon, a superlaser, with enough power to destroy an entire planet. Or does it? Welcome to my channel. This is Science vs. Fiction, the Death Star. The Death Star is a 120-kilometer diameter battle station powered by a Hypermatter reactor. It contains 110,000 laser cannons, 1,000 tractor beams, 1.2 million Imperials with naval and army garrisons, as well, of course, as 8 giant Kyber crystals that create the most powerful laser in the galaxy. Now, a station like this could only be made more terrifying by being equipped with a Class 4 Hyperdrive, allowing it to travel through hyperspace to any location in the galaxy and obliterate an entire planet. So is there any science in this fiction? Well, coming up in this video, I'm going to be talking about hyperspace and hyperdrives, hypermatter reactors, superlasers, and of course, I'll answer the question, could you actually destroy a planet with a laser? Hyperspace is one of the most famous methods of space travel in science fiction, and it's essential to the Star Wars universe. But did you know that this idea both exists in physics and existed in science fiction long before Star Wars? In general terms, hyperspace refers to an alternate dimension of space, and it first appeared in science fiction in 1931 in John Campbell's story Islands of Space. A quick little side note here is that this guy is actually the godfather of the golden age of science fiction. Hyperspace is generally seen as a shortcut through space. So instead of traveling in a straight line from point A to point B, in hyperspace, dimensions are folded or crumpled in ways that makes the path from A to B much shorter. I don't think anyone's ever going to be able to convince me that it's not just a wormhole, and here's why. The term hyperspace first appeared in 1866 in science, and it meant imaginary space of more than 3 dimensions. Nowadays, the term hyperspace isn't really used in physics, but the idea does remain. So concepts like Kaluza-Klein theory and string theory rely on the existence of many more dimensions of space. We just can't see them. You see, if these other dimensions really did exist, they would be so small that we continuously travel across them without ever noticing. Think about walking along a beach. Now try to find a way to imagine the sensation of walking across a single grain of sand. We just can't. It's so small that it's irrelevant to our experience of the space around us. So these concepts, Kaluza-Klein and string theory, they generally refer to compactified or curled up dimensions, teeny tiny ones existing in our universe, but we just can't see them. But there is another one, and it's found in brain cosmology, and that's brain spelled B-R-A-N-E. Now this concept relates to one singular dimension existing that is larger than ours. Now this higher dimension that we also cannot experience because we can only see and feel in 3 dimensions, this higher dimension is referred to as the bulk. Our universe would be the brain, which exists inside the bulk. Now the bulk is basically hyperspace. There are even some models that suggest that the singularity of a black hole could pierce bulk space, and if it met the singularity of another in this space, it would create a wormhole. This specific idea of traveling through bulk space via a wormhole is one of the central concepts in the movie Interstellar. The science of this movie was written by Nobel Prize-winning physicist Kip Thorne, and you can check out my video all about the science of Interstellar if you want to know more. But coming back to Star Wars, hyperspace is presented as a separate higher dimensional space where ships can travel faster than light, and it appears to combine both shorter routes and faster than light engines. Now, to navigate a region like this, you need to be able to map hyperspace, because remember, it has another dimension of travel, so it would have a different layout than our universe. You need an extra coordinate. Without the right coordinate, you could exit hyperspace into a star, maybe even a black hole. This is why navigators are so important in Star Wars, and also it's how the Millennium Falcon was able to do the Kessel Run in less than 12 parsecs, because it mapped a shorter route. Now, while we know that no mass can travel with a speed faster than light in our universe, we don't know what the rules of hyperspace could be. And this is what makes it such a compelling tool for exploring the galaxy, and galaxies far, far away. But if we want to get into hyperspace, we're going to need a hyperdrive. A hyperdrive is a fictional propulsion system that allows a ship to enter hyperspace and achieve faster than light travel. In the Star Wars universe, hyperdrives come in different classes, with higher classes capable of faster and more precise jumps through hyperspace. The Millennium Falcon is famously the fastest ship in the galaxy, and it has a Class 0.5 hyperdrive. Now, a Star Destroyer has a Class 2 hyperdrive, and the way that they describe it in universe is that a Class 2 will take twice the base time to travel a route, while the Class 0.5 will take half the base time to travel. I can't figure out what the base travel time is, though. It seems quite unclear, but overall we can just say that the lower the number, the faster the ship. Now, the Death Star is equipped with a Class 4 hyperdrive, and this is due to its size, making it more difficult to maneuver through hyperspace. Its backup hyperdrive is Class 20, so it's not going to be chasing anyone down, but then again, it doesn't need to, does it? Not when its purpose is to destroy an entire planet. How exactly they break through to hyperspace is not really clear. It seems that they have to travel at FTL to break the barrier, but as we know nothing with mass can travel that fast, there really isn't any mechanism in real science that would explain how a hyperdrive could work in this sense. However, given that the focus is on how much energy it can produce, it may work similar to the concept of warp drive or a wormhole, by creating a large enough energy density to break the barrier between dimensions. Now, I'd assume then that the hyperdrive class may be related to how well the ship's reactor can produce energy, or how well the hyperdrive can harness and use that energy. So where is the energy coming from? We know that the Death Star is a battle station the size of a small moon. It has a hyperdrive, it has ion drives, it's got 110,000 laser cannons, 1,000 tractor beams, 1.2 million personnel, as well as a gigantic planet-killing superlaser. Where does it get all its power from? Now, throughout the ever-expanding Star Wars universe, you will find a variety of starships. The technology tends to be either plausible, things like maybe fission or fusion reactors, a bit of a stretch, something like an antimatter reactor, or entirely fictional hypermatter reactors. But they all rely on the same principle. Something goes in and energy comes out, and how much energy depends on what you're using. Now, this is why when it comes to spaceships, the quality of the fuel is what's important, because you want to get the most bang for your buck. You want the largest amount of energy out for the smallest amount of fuel you can put in. Now, apparently, some of the smaller non-hyperdrive ships in Star Wars will use fission or fusion reactors. Now, fission reactions split atoms apart. Fusion combines atoms together, but both result in some of the mass being converted to energy. Using this for space travel is entirely plausible. Not with today's technology, but it's not hard to imagine a future where ships could rely on fusion reactions to generate a more effective propulsion system. However, even the output of a fusion reactor, that's not going to be enough power for a battleship or a hyperdrive. This is why some brave souls may have opted for an antimatter reactor. Now, antimatter, it's a very real thing. It's the exact same as normal matter, but with a different charge. So where an electron has a negative charge, its antiparticle, the positron, has a positive charge. When we achieve fission or fusion reactions, only a portion of the mass of the atoms is converted to energy. The rest is converted to other atoms and particles. An antimatter reaction is different. You see, when an antiparticle collides with a normal particle, they annihilate. This means that the mass that makes up both particles is converted to pure energy. No extra byproducts. A perfect conversion. There is no energy lost in this process. It's extremely efficient. So of course this is an ideal way to power a ship in science fiction. In reality, it's much harder to imagine antimatter being used for space travel. You see, this annihilation happens as soon as an antiparticle touches a normal matter particle. So it has to be stored in a really specific way, suspended in a vacuum. Now this can be done using electric and magnetic fields, but the more antimatter you have, the larger your containers will need to be, and if they fail, well, just 0.5 gram of antiparticles is enough to cause a nuclear explosion the equivalent of a hydrogen bomb. So yes, you'd get more energy from an antimatter reactor than from using fusion, but it's a lot more volatile. And besides, if you want to push a Death Star into hyperspace, you're probably going to need an entirely new way to generate energy. You need a hypermatter reactor. The history of hypermatter in Star Wars canon goes a little bit like this. The inner planets of the Red Hearn system cracked open, exposing the core to toxic rays from the Red Hearn star. This transmuted the cores of the planets into exotic new materials, which became the building blocks for hypermatter. Now, a rare form of this hypermatter is used in hyperdrives, and this is coaxium. Is this a real element? No. Could it be a real element? Maybe? Some of the ideas around coaxium reactions are similar to antimatter. It's volatile, highly explosive, requires special containers to store it safely, and it has enough energy output to mimic matter-antimatter annihilation. One problem though, there's never any mention of anti-coaxium. And given how rare antimatter is in our universe and how hard it is to make, it's only logical to conclude that coaxium has to be something exotic, something unknown to us. So what could it be? Now, back in the 90s, an astrophysicist named Curtis Saxton started writing some really excellent unofficial Star Wars technical commentaries, which you can find here at theforce.net. One of the topics he covers is hypermatter, and it is just chef's kiss, science meets sci-fi. So the way he describes it is, hypermatter would consist of intrinsically faster than light subatomic particles, which must release all their mass energy as they accelerate towards infinite speed. Faster than light subatomic particles. We're talking about tachyons. Tachyons are hypothetical subatomic particles. Now what this means is that they may or may not be real. You see, the concept of a tachyon doesn't violate the theory of relativity, but we just have no evidence to suggest that they actually exist. So it's a possibility, but it's highly speculative. Now you've probably mostly heard about tachyons in relation to time travel, thank you Star Trek, but using them to create energy, it's so clever, and here's why. All the particles that we know travel at speeds less than the speed of light, this cosmic speed limit that's set by our universe for all matter. Now we can get close to the speed of light by adding energy to accelerate particles, but the closer we get, the more energy we need to add, until eventually the amount of energy required to reach the top speed would be infinite. Now relativity tells us that an accelerated particle traveling close to the speed of light has a larger mass energy than when it's moving at a non-relativistic speed. This is Einstein's E equals mc squared formula. Particles traveling relativistically have more energy than the same particle traveling at a normal speed. Now a tachyon is a particle that only exists at speeds faster than light, faster than this speed limit, and its properties are like a mirror reflection of normal particles. You see, the same rules apply. A tachyon traveling at close to c has more energy than when it's at a normal speed, but a normal speed for a tachyon is much faster than c. For us to move away from c, we slow down, we lose energy. A tachyon would speed up, but it still loses energy. Remember, it has the most possible energy when it's at c. So instead of slowing down, it speeds up towards infinity. And when it's close to infinity, it barely has any energy left, nothing that would have any influence on our universe. So if you could accelerate a tachyon to an infinite speed, it would release all of its energy on the way. And this would be like converting its entire mass to energy similar to antimatter annihilation, but without needing the antiparticles. Finally then, if you have a reactor that can accelerate these exotic particles in this way, then the power output that you get would depend on the rate at which the reactor could harness this release of energy, or how close the accelerator can get to infinity, leading to different classes of hyperdrive. Maybe. I told you it was clever though. So to summarize, the central core of the Death Star is a hypermatter reactor. This relies on the total annihilation of tachyon particles into pure energy via particle acceleration towards infinity. This is what gives the biggest battle station in the galaxy enough energy to power a superlaser. 60 years before the laser was invented and governments started working on directed energy weapons, H.G. Wells was writing about invading Martians with heat rays. 30 years before, E.E. Smith was writing about disintegrator rays. And in 1950, just 10 years before the laser was created, Isaac Asimov brought us his stunner weapons. Now, these were handheld devices that emit a beam of light that would render a person unconscious. Does that sound familiar? Star Trek was not the first to set phasers to stun. Now, light is something that we have interacted with our entire existence. But an intense beam that could cause damage to objects and people, that was science fiction. Until. Back in 1954, Charles Townes and Arthur Shallow invented the maser, microwave amplification by stimulated emission of radiation. Now, this got Townes wondering if you could do the same with visible light. And 4 years later, in 1958, Townes and Shallow, along with Gordon Gould, independently conceived of a way to create the first optical laser. But it would be Theodore Maiman in 1960 who would actually achieve it. Now, this is how science works. It's not always the ones with the idea that actually make it happen. So how does a laser work? Light amplification by stimulated emission of radiation. So we start with what's called a central gain medium. Now, it can be a gas, it can be a liquid, maybe a semiconductor, but it's usually a crystal. Maiman's original laser used a synthetic ruby crystal. Now, this gain medium is what amplifies the light. You do this by exciting the atoms in the crystal, give the electrons more energy. But over time, the electrons will naturally want to return to their original energy state, their ground state. Think about it like this. You might fancy going for a run, but eventually you'll want to slow down and just walk or, sit. So when these electrons move back down, what happens to this extra energy? Well, it gets released. It physically leaves the electron as a photon, a tiny packet of electromagnetic radiation, light. So the process of an electron moving to a lower energy state results in the emission of radiation. This is a natural, spontaneous process. And how long it takes depends on the atoms in the crystal and the wavelength of the light. But we want to force this to happen. So we apply energy in a way that stimulates the excited electrons and forces them to release their energy and drop down. This causes stimulated emission of radiation. If your crystal is in between two mirrors, you create what's called an optical cavity. So when you stimulate the electrons to emit photons, they bounce back and forth between the mirrors. And each time they pass through the crystal, they stimulate the emission of more photons, releasing more and more radiation, amplifying the light. Finally, when you reach a specific point, when you have enough built up, a beam of light will be released from the cavity, and this is your laser beam. When Maiman achieved this with a ruby crystal in 1960, our entire world changed. Lasers are instrumental in so many parts of our lives: communication, medicine, manufacturing, environmental and remote sensing, scientific research. And this initial boom of laser technology went down the exact route that science fiction had envisioned: directed energy weapons. Let's talk about space lasers. And by that, I mean the Strategic Defense Initiative. This was nicknamed the Star Wars program because apparently politicians either think they're funny or nerds really are ruling the world. Anyway, the Star Wars program was officially established by Ronald Reagan in 1983, but it was something that had been brewing for decades. The concept of space-based lasers was established pretty much from the moment the laser was invented. But the technological requirements were, and still are, beyond our ability. After World War II and the development of nuclear weapons, and after the space race, the US and USSR were in a Cold War. Now, the concept of mutually assured destruction was well established, but nobody was particularly comfortable with it. Everyone was looking for the next stage of defensive weapons. As part of this strategy, they hoped to use space and ground-based lasers as a method of ballistic missile defense. Basically, they wanted to use lasers to shoot nuclear weapons out of the sky. Now, the first country to establish this defense system would essentially remove the MAD doctrine and potentially incite a nuclear war. The problem with all of this is that the Star Wars program was focusing on a field of science that was brand new and not yet well enough understood to promise space lasers. Edward Teller, though, of hydrogen bomb fame, he was adamant that there would be a powerful enough X-ray laser within 5 years. And there was not. After over a decade of research, plus millions and millions of dollars, they eventually found out two things. Firstly, the technology was not and still is not advanced enough to provide a high-power laser that can track a ballistic missile and maintain contact in order to penetrate it. And second, in order to have any amount of power that is capable of even slightly damaging a piece of metal in the air, it required a laser system that was the size of multiple warehouses. A Death Star, maybe? Since then, there have been huge advancements in laser power, and it does continue to improve. But space lasers as a defensive weapon, it's not really in our near future. But maybe if we had some Kyber crystals and a Hypermatter reactor? Kyber crystals are not real crystals, but in a galaxy far, far away, they are particularly well suited for use in focusing and amplifying energy beams. And this makes perfect sense because we know that to create a laser, it depends on the material that's used for the gain medium. So let's try to figure out what we can learn about a Kyber crystal. We know that the Death Star superlaser must be in the visible portion of the electromagnetic spectrum with a wavelength range of about 510 to 570 nanometers because it's giving out green light. We also know that its power is recorded as 10 to the 33 watts. That is a lot of power. Now, if we look at lasers in terms of power, ones you can buy, things like laser pointers, they're normally in the milliwatt range. Ones that would be used commercially or maybe in research labs all over the world might be around 100 watts. And then there are high power lasers. Now, there are only a handful of these around the world set up in special facilities that are designed to produce and handle power up to petawatts. That's 10 to the 15 watts. The scale goes something like kilo, mega, giga, tera, peta, which is kind of where we are in laser science. And then for context, the Death Star is kind of like up here somewhere. High power lasers can use a few different mediums to amplify the laser beams, but two of the most common types of crystal used are Nd:YAG crystals, which stands for neodymium doped yttrium aluminium garnet. It's a lot. And TiSAF crystals, which are titanium doped sapphire. And of course, the Death Star uses Kyber crystals. So what makes one crystal better than another? Or like what properties might a Kyber crystal have to have that would make it better than the other ones that we know of? Firstly, it should have a high transparency. So this means that we don't want the crystal to absorb or scatter any of the photons. We want to get as much of them as we can. Secondly, it will need to have a high resistance to mechanical stress, so it can't deform or break apart under the pressure. Thirdly, it will need to have a high thermal conductivity, so allowing a lot of heat to pass through it without deforming or melting. Truthfully, there's a lot more complicated stuff that we just don't need to know right now, but what we can say is that for the Death Star to have a super laser using green light, it has to have a gain medium, a crystal, that can let the light easily through, that won't break or melt due to the stress and heat from so much power. Now, we don't currently have a crystal that's going to do what the super laser can do, but maybe a long, long time ago in a galaxy far, far away. How powerful is the Death Star's super laser? The super laser is actually 8 lasers combined, and beam combining is absolutely a real thing. It's regularly used to create more powerful lasers for applications like laser cutting, welding, materials processing, as well as in scientific experiments. The most common method of doing this is spatial combining, and this is when multiple laser beams are physically overlapped in space and time so that they converge into a single beam. Now, this is often done using things like beam splitters, mirrors, optical components to align and merge the beams. So I will take this moment to point out that the Death Star at no point appears to have any optical components of any kind. However, I'm choosing to ignore this completely and act as if they are there. Now, when you combine beams, it's not going to be perfect. There will be some optical losses. There will be some issues with beam quality and alignment, as well as a few other things, but in general, you can expect a conversion efficiency of 70 to 90%. Now, the Death Star at full charge is apparently 3.9 by 10 to the 33 watts for reference. That's more powerful than our sun. Now, if that's 70% of the power of 8 beams combined, then each laser beam has to be around 7 by 10 to the 32 watts. The most powerful lasers in the world are petawatt, 10 to the 15. So each Death Star beam is individually like 100,000 trillion times more powerful than our most powerful lasers. Now, you might think that I'm reaching by saying that the Death Star is not too hard to imagine. But think about it this way. You have a reactor that generates a lot of energy. You have a crystal that has special properties allowing to generate very large, high-power laser beams. You apply spatial beam combining to create one giant super laser with more power than the sun, and then you aim it at a planet. Like it's hard? Okay, of course you do need hypermatter and special crystals, but those are just scaling problems, really. Now, after all of this, though, there is just one question left. Would it work? Let's see if we can destroy a planet with a giant laser. Now, there are 5 things that could happen. Firstly, we have ionization and expansion of the atmosphere. So if you apply the right wavelength of light, you could ionize the planet's atmosphere or its outer layers, causing a rapid expansion or explosion, which would strip away the planet's atmosphere, or at least cause significant surface damage. Now, this wouldn't break apart the planet, but with no atmosphere, it wouldn't be habitable. Now, this probably isn't happening with the Death Star, because we're using a green laser, which is from the visible portion of the electromagnetic spectrum, and this type of radiation is non-ionizing, so it just wouldn't do the job. Our second option is resonant frequency of vibrations. So all materials have a resonant frequency, and this is a frequency that it naturally oscillates at. Now, if you have a laser that is tuned to the resonant frequencies of, say, the planet's core or the materials in the crust, well, this could potentially induce vibrations causing structural failure. Think about how an opera singer can shatter a glass by singing at its resonant frequency. The only problem with this is that it would have to be really specific to a material, which kind of would make the Death Star obsolete for a number of worlds, and I just don't think the Emperor would be happy with that. Our third option is heat and thermal expansion. So the laser could be used to heat the planet's material to extreme temperatures, causing thermal expansion. Now, if the heating is rapid and intense enough, it would have the potential to lead to structural failure of the planet's crust or mantle. Now, unlike the case of resonant frequencies, this doesn't rely so much on the properties of one material. Instead, we could affect many materials, so long as their tolerance to heat is lower than what the laser can provide. But it might not tear the planet apart, it would more likely just leave a hole. Our fourth option is molecular disruption. Now, at a high enough intensity, the energy from a laser could break molecular bonds. Now, this would disintegrate complex molecules into atoms. To do this to a planet, you'd have to focus on the key components of the planet, so things like water molecules, atmospheric gases, the core materials. Essentially, you want to disrupt the chemical and physical integrity of the planet. Now, this is more promising than the others, but you would still need the atoms to fly far enough off that they don't get pulled back in by the gravitational energy of the mass. So really, what we need to do is break gravity.
Caught in the gravity field.
Caught in the what?
Mavity field.
We've got Mavity.
Mavity well or?
Mavity.
Gravitational disruption. We want to destabilize the gravitational equilibrium of the planet. Now, if we can do this, then the planet will tear itself apart due to gravitational forces. Now, the gravitational binding energy of a planet is kind of what holds it together. So it tells us the minimum amount of energy needed to disperse a planet's mass so that gravity wouldn't be able to hold it together anymore. The energy formula for this takes the mass of the planet and the radius of the planet into account, along with the gravitational constant. So for Earth, the mass is 5.9 by 10 to the 24 kg, and the radius is 6,371 kilometers. So for an Earth-sized planet, the energy that would be required is 2.2 by 10 to the 32 watts. This energy is lower than a single one of the Death Star's laser beams. And for those of you wondering, yes, Alderaan is around the same size as Earth. It has a diameter of 12,000 kilometers. Now, at this stage, I feel like it's my duty as a physicist to point out that this is all highly speculative, and there is absolutely no guarantee that it would actually work. Put down the tools of the Empire. But what we have learned today is that if you have a hypermatter reactor that can energize Kyber crystals, which work extremely efficiently with green light, then you can combine multiple high-power laser beams into one superlaser with more power than the gravitational binding energy of a planet, and then you might, just might, have the galaxy's deadliest weapon. Listen, no one will be able to stop you, unless of course they, hear about those thermal vents that you've built all over the battlestation. Oops. I'm Abby. First off, if you're still here and seeing this, then thank you so much for watching. I really love getting into the science of this stuff, and I hope you enjoy the deep dive into nerddom too. Now, over the next while, I'll make supporting shorts and videos to answer any questions that you might have about the science of the Death Star. So let me know what you'd like to know and follow along if you liked this. Oh, and like this if you liked this. Thank you.